Okay. Thank you, everyone, for joining today's Linux Foundation Decentralized Trust virtual meetup. We welcome your comments and questions. We're also live streaming this right now, so anybody watching the live stream is welcome to look in the comments for dial-in information about how to join the discussion if you're curious to take part in the discussion. And all we ask is if you participate, that you please be respectful to one another. We operate these events under our code of conduct. There's a link here if you want to find out more. And with that, I will hand it off to our presenter today, Daniel. And Daniel, thank you for putting this together, and we're looking forward to the discussion.
So, hey everyone, let me just share my screen. So, hey everyone, this is Daniel, and this is practically a meetup on zero knowledge proofs. While actually it's a learning group throughout this year, and it was throughout last year as well. We just cover many different topics around zero knowledge proofs, ZK and Snark, mostly from application development and programming perspectives with limited theory. Actually, I'm myself more like a software developer or software engineer, not necessarily a mathematician. So we just try to cover theoretical topics on a very high level basis. So the agenda for today, we just start with the zero knowledge learning groups logistics. Then basically I just build up the presentation in a way that even if you just did not necessarily see the last few sessions, it might make sense as a block or as a standalone presentation as well. So basically I usually start with zero knowledge proof summary. I continue with like high level flow of zero knowledge programming. Then we just summarize a little bit Stark, although we had like a full session last time on Starks. Then I will just cover a little bit like Reed-Solomon's codes, Merkle trees as vector commitments, and we take a look on FRI concepts and FRI workflow. There's going to be a link to a demo. Due to time limit, we probably not going to cover the demo, some challenge links and resources, and we'll see how much time we will have for questions and answers. Anyway, the whole presentation gonna be shared basically, so you will find all the slides and all the recordings on YouTube, and then I will just show in the logistics where you find other materials. So basically, that's the idea for this zero knowledge learning group. That's the logistics. What we do, we just do one session each month. Basically, there were some brainstormings that we do like, every second month, but I think I will manage to have practically each month. It was done basically throughout the year, last year as well. So this is kind of a continuity of the last year structure and presentations and topics as well. Basically, the idea is that this is like one meetup each month. It's like usually the third Thursday or the fourth Thursday of each month. And then what I'm doing, I will give like a brief presentation on different topics, and then you will find a lot of materials that you can work on an individual basis. This year we might as well have some guest lecturers as well. So if you're interested to give like a lecture or a presentation on different zero knowledge proof topics, then you are more than welcome. Just ping me basically, and then we can just arrange it. It looks that year, so we have like different topics, and then basically we usually start in a way that we start with theory. Again, I'm not a mathematician, so we're not gonna go deep into figures. Basically, I will just cover the mathematical concepts on a very high level basis. But despite, I mean, the first like 2 or 3 months or sessions are more like theory oriented. So basically, this year we started with Starks, and then I continue with FRI. And probably we're gonna stop with like theory. So from April, we just continue with our next block, which is more like programming, introducing like different zero knowledge programming languages and platforms. We covered last year Circum and another programming language, and this year we're just gonna cover probably like ZK Sync, Zinc, Leo, or perhaps Starkware as a platform. So basically, we will have like 4 presentations on different zero-knowledge programming languages and platforms from a more programming perspective. And then the last year or last part of this year will be like applications. So there will be like one application on each different like possible one presentation on each different interesting application, like zero knowledge bridges, like zero knowledge virtual machines, perhaps zero knowledge identity. There might be a different presentation on verifiable credentials. I mean, especially if you take a look on the presentation part of verifiable credential, that's like a zero knowledge proof supported element, and there might be something on voting or how you can create voting algorithm with the help of zero knowledge proofs. So that's the logistics. But basically, if you have like any wishes like on different topics that you want to include in this year, then yeah, just ping me, just drop me a comment basically, and we can take a look if I can prepare. And again, if you just want to do like a guest lecture on different zero knowledge proof topics, you are more than welcome. So from a technical point of view, it looks that way, that most of the coordination is done basically in a Discord channel. So there's a Discord channel for Linux Foundation Decentralized Trust. If you do not have like access, or if you're not part of the Discord channel, you can just Google it. Just Google it, LFDT Discord channel, and basically the first match is like an invitation to the Linux Foundation Decentralized Trust Discord channel. So you can just join to the Discord channel. And if you're in the Discord channel, then there's like a session which is called Communities. And under Communities, you find the Zero Knowledge Learning Group. And then basically in the Zero Knowledge Learning Group, I will post everything that I have related to this learning group. And basically, if you have like any questions, comments, or ideas that we should cover throughout this year, then just I mean just make a comment here. Just post a comment or post an idea here. That's the like logistical part of this Zero Knowledge Learning Group. There's a GitHub repository as well. Sorry, I mean there's Meetup, of course. So basically, each of these session is announced on meetup.com. You will find like many like Linux Foundation Decentralized Trust meetups throughout the world, and then basically, as this is like an online event, you will find these meetups in practically in each different meetup group. And then there's a repository as well. The repository is under Linux Foundation Decentralized Trust Labs. So basically, it's a lab, and it summarizes the content practically for this whole zero knowledge learning group. So basically, again, this is like the second year. We started at the beginning of last year. So we have like, syllabus practically for 2025. For each month, you will find the presentations, you will find the slides, you will find the meetups. If there were some demonstrating a code or developer challenges a code, you will find the code as well. So basically, the code can be found here as well. You will find the documentations, and you will find all the literatures and stuffs basically. And that's the same for 2026 as well. So we started somehow in January on Starks. There were no codes or coding exercise. We are somewhere here with FRI, that's fast Reed-Solomon IOP of Proximity. And you're gonna find all these slideshows, meetups. You will find the recordings here as well, but you find the recording under Linux Foundation Decentralized Trust YouTube channel as well. There's not gonna be code, not much challenge today, but basically you will find all the links and literatures. And basically, as I mentioned, the next one gonna be like a German version of this learning group. But after that, you will find more like on a pragmatic and programmatic way or stuff, how you can do like zero-knowledge proofs or how you can program zero-knowledge proofs. So that's the logistics. And then let's just start with like summarizing zero-knowledge proofs. Anyway, today's presentation is gonna be like not 1 hour, probably just 45 minutes due to some of my time constraints. So we're not gonna cover code, we just cover the ideas on a pretty high level basis. So what's the zero-knowledge proof? Basically, generally, we have like two parties in cryptography, like Alice and Bob, and then sometimes there's like the evil Mallory as well. But just in a simple setup, we have like these two people. Alice is the prover and Bob is a verifier. And Alice tries to prove something to Bob in a way that Bob will be sure that Alice really knows something, but basically this fact, which is known by Alice and proved by Alice, will be not known to Bob. That's like the basic idea for zero-knowledge proofs. One idea is that just imagine that Alice wants to prove that she knows a pre-image of a hash function in a way that Bob is really convinced that Alice knows the pre-image of hash function, but basically Bob will not know the pre-image of the hash function. That's like a zero-knowledge proof. Another intuitive example is like this Sudoku in the middle of this picture. So you can imagine that this is like a Sudoku puzzle, and Alice can solve this Sudoku puzzle and wants to prove to Bob that she can really knows like a solution for this Sudoku puzzle, but she wants to prove it in a way that Bob will be convinced that Alice really knows like the solution for this puzzle, but basically this solution will be not revealed to Bob. So that's like the basic idea for zero-knowledge proof or proofs. Generally, if you think of like ZK proofs, usually we can express many different problems. I would say many different domains or domain problems as zero-knowledge proofs. So basically, to describe these different like domains or domain problems, we have something which is like a computation model. And the computation model is a little bit like tricky and mathematical. It's usually like an arithmetic circuit. It's a circuit practically on a finite field with like plus and multiply gates. And you can, I mean, theoretically, you can express a lot of things with this model, even if it is not necessary, very practical to write like arithmetic circuits practically by hand. But anyway, as a general idea, we can think of arithmetic circuit is like a tool to express different domain problems. And we have like this arithmetic circuit, which has some inputs. We can have like public inputs and we can have like private inputs. Private inputs are practically like the pre-image of the hash function or like the solution of this Sudoku puzzle. These are private inputs and these are the witnesses. And then we can evaluate this circuit, this computational model with public and private inputs. And we can have like, I mean, either a value or more specifically, it's more like a predicate. So we can have like a true or false value. So that's actually the computation model. And then to be like a more formal, it's not exactly formal, but like a more formal, like the general idea, we can say that we have two roles, not just Alice and Bob, but we have a prover and we have a verifier. And the prover, which is Alice, is an algorithm, and the verifier, which is Bob, is an algorithm as well. So prover practically gets the public input and the private input and perhaps some more elements. And then she creates a proof. And basically the verifier gets the public input and the proof itself. And additionally, sometimes plus additional parameters as well. And the verifier either accepts or rejects that proof. So practically, public input is like, I don't know, in the Sudoku puzzle, perhaps the public values are the public inputs. So like this 1 and 3 and 5 and 6 or 9. These are like the public values, and the private values are really the solution of this puzzle. And then basically what's important that at creating the proof, both the public and the private values are considered for creating the proof. But of course, in the verification, only the public inputs are visible to Bob. So he gonna be convinced that Alice really knows actually the solution of this puzzle without actually knowing these private numbers here, which is practically the solution. So we can have some properties for zero-knowledge proofs that we want to use. So first, it is so-called succinct. Succinct means that the size of the proof is small. Sometimes it's just constant. Sometimes it's just logarithmic. And the verification algorithm is fast as well. Because otherwise it might not make much sense basically for these proofs. But if we have like fast proofs, small proofs that are fast to verify, then we can find a lot of applications. And there are some other properties as well. It is like sometimes complete. Complete means that if Alice really knows a fact, practically like the solution of the Sudoku puzzle, then she can convince Bob that practically Bob gonna accept that proof, or at least accept with a very high probability. And then there's this knowledge soundness, which is the other direction, which means practically that if Bob basically accepts a proof, then Alice really knows a fact based on that proof was generated. So that's like knowledge soundness. And zero knowledgeness means that basically based on these interactions, anyway, this is like an interaction. It looks that way, that it might not be just a one-step interaction, but there might be like several steps of communication. But zero knowledgeness means that based on these several steps of communication, nothing revealed to Bob on the private input on the witnesses. So that's like the basic idea of zero-knowledge proofs. Perhaps it's just important to mention that, I mean, zero-knowledgeness is actually like an optional property. We might not need it because there are some applications where we just use that the proof itself is succinct, is small. So basically in situations, we can use this whole structure to prove that there was like a complex computation, and the complex computation and the result of the complex computation can be verified practically with the help of a small proof, which is easy to run. So this is actually like an important property, even if we don't have like private inputs, even if we just don't have like zero-knowledge properties. So going a little bit to the high-level flow of zero-knowledge programming, usually it looks that way that, I mean, I mentioned here that we have kind of a computation, which is like an arithmetic circuit on a finite field having plus and multiplication gates. But practically nobody likes programming with arithmetic circuits. It's actually not very much natural for human intelligence. So generally, we have like a more complex flow. And then it looks that way that usually we start with like high-level programs. We have something which is like a high level. It might be a domain-specific language. It might be something which is a Rust-like program. But basically, it's just more closer to human intuition. It's just easier to program. It can be developed by by a software developer or programmer as well, with sometimes with some a little bit like cryptographic background, but basically this is like a high-level program, just like any kind of high-level programs. And usually we start, I mean, if we have like a full platform, usually we start expressing our domain problem with the help of this high-level program. And then there's a compiler that compiles our problem to like an intermediate representation, which is usually something which is like an arithmetic circuit, or we can say that like an arithmetic constraint system. These can be expressed as equations on finite fields as well. And this is like more abstract and more mathematical. And actually the idea that we need like this arithmetization, this arithmetic constraint system or arithmetic circuits, is because we just want to have like one more step from that. Basically, what we want to do, we want to work on a mathematical basis with polynomials on finite fields. And like an arithmetic constraint system or like an arithmetic circuit is pretty far for polynomials, or it can be like easier, translated to like polynomials. And basically we will have as we have like polynomials, we have all the core mathematical algorithms and core zero-knowledge proof systems on a deep dive, basically with the help of these polynomials. Anyway, I'm not gonna have polynomials in this presentation, so again, it's gonna be like without figures, but yeah, so these concepts are sometimes a little bit like tricky. And if we have like polynomials, usually we have like two systems or two ideas. First, we have like a polynomial commitments. Again, if I say polynomial, you can think of like a computation on a very low level, an abstract computation, which expresses like a domain problem, like for solving the Sudoku puzzle. And that is compiled to like arithmetization, eventually to polynomials. And this full computation is like expressed by polynomials. So we can have one step, which is like a polynomial commitment. In this step, the prover just commits somehow one polynomial, like Alice commits one polynomial to Bob, and then Bob asks this polynomial to open at one point, and basically Alice needs to present like the opening of one point with a proof that it was really like an opening of a certain polynomial. So that's something that can be done. And basically, based on polynomial commitments, we can create like more structured algorithms as well, which are like polynomial interactive oracle proof that practically not just one polynomial, but committing several polynomials, and then basically opening these polynomials at certain points, and then at the end, basically making sure that that really the original polynomials were committed and opened at certain points, basically. And based on this low-level representation, we get the zero-knowledge properties. So let's have one slide on Stark. Stark is an acronym for Scalable Transparent Argument of Knowledge. And that's like one area of zero-knowledge proofs. Stark means, again, scalable, transparent, and argument of knowledge. Scalable means several things. So first, both the generation of the proof and the verification time is pretty fast. We spoke just on the verification time, which is succinct, but basically, I mean, the proof generation can be important as well, and proof generation is fast as well. Perhaps just to have in scalable, Stark has like a different computation model. It's more closer to like a classical virtual machine, and not so much like an arithmetic circuit or like a circuit. So it's a little bit like more scalable in a way that you can have like many different programs on a virtual machines, as opposed to like an arithmetic circuit or a circuit model where you practically need a different circuit for each of your models. One other property is transparent. Transparent means that there's no need for an initial trusted setup. The opposite is SNARK, is succinct non-interactive argument of knowledge. In most of the SNARK systems, you need a trusted setup, which is not so optimal, because if anything goes wrong with your trusted setup, then basically anybody can prove anything. And that's practically suboptimal, but in Stark, you don't need this trusted setup. And we have this argument of knowledge. Argument of knowledge is like the prover knows the fact to prove. One important thing, so these models might be interactive and non-interactive. If that's interactive, we get like many iterations. If it's non-interactive, we have just one communication cycle, so Alice just proves something and Bob either accepts or rejects. There's the so-called Fiat-Shamir transformation. With Fiat-Shamir transformation, you can just transform most of the practical interactive proofs to non-interactives. And some other properties as well. Starks are quantum secure. It means that it cannot be broken even by quantum computers, because they are based like on hash functions, and then as far as we know, quantum computers can practically solve faster like hash functions, but basically not exponentially faster. So basically, we consider like hash functions secure under quantum attacks. And the same is true for Merkle trees, basically. So this is like FRI. What we speak of, it's like fast Reed-Solomon IOP of Proximity. That's like the polynomial commitment scheme for Stark systems. So that's what we speak of today. And basically, that's like pretty efficient both in proof size and verification time. Sometimes it's just not so efficient as like SNARK, because like in SNARK, you might as well have like a constant proof size, which is not necessarily true for FRI, but basically, despite the proofs are like small enough. And in the following, I'm just gonna present some of the basic ideas, or some of the core ideas behind FRI. Again, I just did it without like having any quotes. So basically, I would say it will be like the for mathematicians, I would say this will be like the fairy tale presentation of FRI, basically, or some core ideas behind FRI. So first, I have one slide on Reed-Solomon codes, because we say like FRI is fast Reed-Solomon IOP of Proximity. So let's start. Let's have one slide on Reed-Solomon codes. So the idea of Reed-Solomon codes, that's basically from error detection and corrections. So if you have like some kind of a communication channel, and you just wire some message basically, and there might be some interference, then you might lose some of your bits or messages or part of your messages. So the question, how we can just extend this communication in a way that basically your message will be or can be decoded even if there are like some errors, some communications errors in the middle. So that's like generally error detection or error correction codes. And Reed-Solomon code is one of these error detection and error connection codes. So basically what we have, we get like a k-bit input, and it is, that's our core message, and we just extend in a way to like n bits with some redundancy. So there will be like n minus k redundancy. So the idea is the following. Basically, we work with like polynomials, of course, because that's the core of this whole field, fortunately and unfortunately. But basically, the idea, let we have like a message of 4 characters or four numbers practically. So these are the, like, this is our first character or first number, this is our second number, this is our third number, and this is our fourth number. So what we can do with like 4 such a points, basically, that based on these 4 like black points, we can just create a polynomial, and the polynomial of degree 3. So basically this gray line, based on these 4 black points, which is like our core message, is like a polynomial practically of degree 3. So generally with k data points, we can have like a k minus 1 degree polynomial. And supposing how we can create this polynomial is a little bit like more tricky. It's the so-called Lagrange interpolation of like, it's like creating a unique polynomial of degree m minus 1 on exact points. And it's just n log square and time complexity. But you can think of like Fourier transformation or fast Fourier transformations. These are just similar algorithms for creating this polynomial. And as soon as we have this polynomial, what we can do is that we can just extend these 4 points like with 3 additional ones. And again, these 3 additional ones will be on the same polynomial. So practically we have our first, second, third, fourth, fifth, sixth, and seventh number, which are like characters in a message. And with that, we can send these 7 characters from the receiver to the sender. Sorry, from the sender to the receiver. And then basically what the receiver can do, if the receiver gets like at least 4 points, and it doesn't matter which 4 points, supposing like this one and this one and this one and this one, and like this point and this point is missing due to some noise in the communication, the receiver can, based on like 4 points, create this polynomial. And basically, if the receiver has the polynomial, then the polynomial is the same based on like 4 points. That was the polynomial of the sender. So basically, can infer which was like the first character, the second, the third, the fourth, the sixth, and the seventh, and so on and so forth. So that's somehow the idea of Reed-Solomon codes, and that's somehow the ideas how it can be done by error correction or error detection codes. Okay. Perhaps what's important here is not necessarily how it is used in error correction codes, but basically that there's like certain points, and for certain points you can just create like for k data point a k minus 1 degree polynomial, and you can extend some other points as well. So that's like more important in FRI. So another point for this one is like kind of an idea how we can commit one polynomial. It's again it's gonna be just a very general, very intuitive way. How we can commit like one one function or one polynomial from the prover to the verifier as a polynomial commitment scheme, and how the verifier can ask the prover to open this polynomial at one point. Again, I will just to have the context, we are somewhere here at the bottom of this whole programming flow. So we are somewhere here to create like polynomial commitments. So basically we have one computation which is one polynomial, and just we want to commit from the prover to the verifier, and the verifier wants to like open this polynomial at one point, and the prover needs to convince the verifier that like there's some input output, so it's really an opening of a polynomial, and then that was really like the original polynomial that was like committed. So what we can do, basically, we can use like a Merkle tree. So so think of that we have like one polynomial, which is like, again, practically one computation of one domain model. And then we can commit it as a Merkle tree. So basically, if we have like one vector, we might as well call it as vector commitment as well. We might as well just have like one vector here. This is like the one vector here. So basically, based on this one vector, we can just hash these elements and hash two of these elements and hash two of the two elements and so on and so forth. So basically, we have like one Merkle tree, and then the prover can send the root of the Merkle tree to the verifier. And basically, if the verifier asks to open this Merkle tree at one point, like at M4, then basically the prover can send like a proof of this, like sending this hash element and this hash element and this hash element and this hash element. So basically, it's like a proof which is like a logarithmic of the size of the tree, and basically that's gonna be like a proof that's like one element is in the Merkle tree. So that's like a classical Merkle tree commitment. We can try to extend it to commit not just a vector but practically a polynomial. And the problem is that we can do in an intuitive way, which is not necessarily the best one. Like if we have like the all possible values of a polynomial of a function here, and then just hash everything together and just send the root it. But basically there are like too many values eventually. So this domain might be extremely huge. But basically with the ideas of like Reed-Solomon codes or like, I mean this Lagrange interpolation, what we can do a little bit in a direction that we don't have like all possible values of our basic domain here, but instead we just have like selected values. So if you think of like with these 4 data points, we will have the whole polynomial basically, and this polynomial, it's usually discrete. So even if it's just discrete, it might have like, few hundred trillions of different data points. But with these 4 data points, basically, we can just express the whole polynomial. And it might be an idea just to commit with a Merkle tree just a selected number of like basic values of the polynomial, and then based on these few values, the polynomial itself can be constructed. So basically, we can infer to all of the other points as well with like the Lagrange interpolation. So one idea is like just select the roots values of this polynomial and commit it with a hash. But the problem is basically generally that even if we use that direction, like proving that one item was in the committed structure might be difficult. It's because basically even the roots can be pretty, I mean, there might be many pretty like few hundred millions of roots in a practical polynomial for Zenich proofs, which are like many values. But the problem is if we have just the values or the like the roots of a polynomial, it might not so easy to create like a Merkle tree commitment for these values. It's just because we don't have all of the values or possible values. So for this one, we use like the FRI practically. So based on these two ideas, I know it's a little bit like high level. Again, I'm just pushing it, the high level ideas, perhaps without structure. But basically, what we do with FRI, it's a fast Reed-Solomon IOP of proximity. We prove that a vector commitment, which is basically a Merkle tree, a kind of a Merkle tree, that we saw last time is close to a Reed-Solomon code work, which is like a low degree polynomial. So practically, it is kind of a Merkle tree of a polynomial, and this polynomial is like the the domain problem, which is expressed in a very low level way. And what we do is that we commit this Merkle tree root practically, and we prove to the verifier that this one is practically the same, or that what was committed. It's a little bit tricky because it's like a proximity proof. So we not necessarily say that's exactly the same, but proximity means something which is pretty near, and usually there's like a one security parameter. So basically, saying that after certain steps or after fine-tuning the security parameter, proximity means that it is very, very near. So from a practical point of view, it is the same. Okay. So it's a linear time prover, logarithmic time verification. And there's one idea which is famous from FRI, which is the folding. It looks that way, that basically it just splits this commitment into smaller commitments recursively, reducing a large Reed-Solomon code testing into a smaller one. And again, it's kind of a trick. It's a proximity proof, so it doesn't guarantee that the data is a perfect code burg, but rather it is close to the original committed function. And again, it's like a security parameter. So after fine-tuning it, we can say from a practical point of view, that's the same. So let me see just in action after this. Again, I did not have like figures, but despite these, I mean, concepts might be not so trivial. But anyway, so that's the general idea for an FRI workflow. We got like two phases. One of the commit phase, and the second one is the verification phase. And we have like two actors. And we got the prover and we got the verifier. So basically, there's an interaction. First, the prover wants to like commit basically like a very huge polynomial. And the verifier, again, committing means basically that there's like a Merkle tree, and then the prover commits just the Merkle tree of this huge polynomial. But basically, this polynomial is so huge that it can't really be verified. So the verifier accepts that, hey, I mean, this is like the Merkle root of a very huge polynomial, but says like, hey, it's just too big to verify. So as a next step, the verifier sends back a random value. And based on this random value, there's the so-called folding. And folding means that this huge polynomial will be somehow smaller. It is reduced in size by factor, usually 2, sometimes more, sometimes 4 or 8 or 16. But the idea is just based on this huge polynomial and some random values, there will be a smaller polynomial, which might be again like a big one. And then the prover commits this big polynomial, this second one, to the verifier. And again, committing practically means that creating like a Merkle tree and sending the Merkle tree root to the verifier. But again, even in this round, the verifier says, hey, it's just too big to verify. So sends back like another random value. And then based on this random value and the second polynomial, there will be again this so-called folding. So creating like an even more smaller or an even smaller polynomial, and so on and so forth. So it might be iterated like a couple of hundred times as well. So eventually there will be like a small polynomial, a small enough polynomial, and this small enough polynomial can be sent to the verifier, and basically the verifier might say that, hey, I mean, this is small enough, I can already verify, and basically there will be a verification step, as in a polynomial commitment. So basically, he can like ask to open this in one point and then check all of the committed big polynomial, smaller polynomial, even more smaller polynomial, and all of the stuffs that were happening here. So that's the idea basically, and that's the FRI workflow in a very, very high level. So again, there's the so-called folding, which is important. It's reducing the size of this polynomial by theoretically by 2, in some practical applications more than 2. There's this folding, sometimes even folding of mixing, is the process of reducing or breaking this polynomial into smaller pieces to reduce evaluation points, and then the degree, actually the degree of the polynomial will be reduced as well, so it's not maintaining the degree. This is like one example here, so it's like one function which might be just somehow restructured it in a way, and there will be like the so-called folded function, and this will be the next folded function, which will be like committed to the verifier with the help of a Merkle tree, and then eventually send the Merkle tree root to the verifier. And that's the so-called committing phase. And basically, there's a query phase. Again, that's like the end of this whole structure. So basically, the verifier checks if the folding was correct. This whole structure, this whole iteration was correct. So basically, the verifier selects a random point in this polynomial, and then checks all the committed Merkle roots that are presented here, and then checks for each round that these folded values were correct, and then the random was really used. And then basically, eventually, if everything is fine, then the verifier gonna just commit basically this whole proof. So that's the idea. As you see, this is like an interactive proof. So there might be like several iterations, but the point is that you can do this interactive proof to non-interactive with like the Fiat-Shamir transformation, and then basically you have like one proof with the same structure as this one. So this was the FRI. Again, I don't know, in a non-mathematical way. I hope it I hope it made sense. Basically, you find a very good tutorial on Starkware. I'm just opening it. It's more mathematical, of course. So you just need a time to evaluate it. But basically, that's a Stark 101, and you can find like examples for the FRI commitment and for the FRI queries as well. So basically, again, this was like the commitment phase, and the queries practically the verification at the end. And as far as I know, you find it even like in Jupyter notebook as well. So basically, you can just test some of the code on your own. Just give me a second. I'm loading it. Anyway, it should work. So you can take a look basically, and you can experiment on your own, and you can find actually more the mathematical parts as well, more in-depth mathematical parts as well. Yeah, it's gonna be somewhere here. It's a pretty good summary and pretty good tutorial. So that was it. I have one challenge. Just take a look at this tutorial, and then just experiment with FRI commitment or FRI queries if you're more interested in the theoretical details. And then basically I have some links and literatures at the end, and basically that was the presentation for today. It was taking a little bit longer than I expected, so I'm just browsing the questions, and then I try to answer as many as I can. Yeah, so there's a question if there's like any resource we should pull up, reference, GitHub repo, and so on and so forth. So there's not much basically. Again, so this was like I would say this was still still the theoretical part of this zero knowledge learning group. I will stop probably the theoretical parts from from April. So in April we see more action. I mean more coding, and then we can like have more fun as developers. Anyway, if you just go to this repository, it looks that way that during the middle of last year we had some developer challenge as well, and you will find like code examples in Circum and Noir, for instance. So that's what we're gonna do practically from April. We covered more theoretical basis this time and last month as well. Uh, so yeah, there's like a YouTube. Everything is just recorded in YouTube. Uh, and then you will find, I think the presentation will be mailed to you as well, but you will find the presentation as well on GitHub and everywhere. There's one comment that somebody is interested more in verifiable credentials. So the point is with verifiable credential, it's not like a full zero knowledge topic, because the idea is interesting, but it has like one part of verifiable credential, or there's one part of verifiable credential which contains zero knowledge proofs, and that's usually like it's the so-called presentation of the zero knowledge of the verifiable credential. So I'm just I will surely cover verifiable credentials, but I'm just brainstorming to have it in a session that we cover, like, I don't know, ZK identity and the presentation part of zero knowledge proofs in one presentation. So I'm just brainstorming it. I just don't want to go very much into like just covering verifiable credentials, because I mean not the whole concept is interesting in this learning group, just the presentation part, I would say. But again, that will be like from August or September. We continue from April with some coding, with some platforms, and we will take a look basically on applications around the end of the year. So basically, that was for today. Again, it was taking longer than I expected. It's just sometimes difficult for me to make an estimation on the time, especially if some of the content is pretty like challenging. So I mean, we can have like time for one more question. So if you have any questions, just in 1 minute, and I will try to answer. Again, this is a zero knowledge learning group, so I wouldn't say that I'm an expert on this topic. I'm learning actually with this learning group as well. So if you have any questions, I will try to answer. Otherwise, I will just post everything under the zero knowledge learning group channel in Discord, under Linux Foundation Discord channel. So if there's no questions, then I would say thank you very much for your attention. We will have the next session in March in German. So if you feel like I don't know, speaking German or practicing on German, there will be a very basic presentation on zero knowledge proofs in German in March. And from April, we continue with coding and different zero knowledge platforms. So thank you very much again, and then see you next month or in 2 months.
Great. Thanks, Daniel. Thanks, everyone.